In this video, we do an exercise which has something where we can play with matrices, and we might need to use some loops in here, but also some smart indexing, I would say. So the idea here is that we recreate a matrix like this for any n, where n actually represents this element on the diagonal. So for this particular matrix, n is 5. But I would like to write a code which does it for any n, so be it 10, 20, 100, and so on. So you can see the pattern in here that n, or this highest element, is always on the main diagonal, and then when we step kind of one row, this diagonal row away from the main diagonal, then we have value smaller by 1 until we reach actual 1 in the corner. And there's a hint here to make use of command I, and this is what my solution will be doing. There could, of course, be a way to do it using nested loops. So, for instance, you would have I going from 1 to n to go through the rows, and then inside for I going from 1 to n as well to go through the columns, and then one by one create these elements, somehow referring the value of this particular element to its location. However, I will do it using just one loop and using this I command. So now if you remember I, for instance, if you say I5, or let's take a smaller one, I, for instance, 3, it creates this kind of matrix which is 3 by 3, and it has 1 on the diagonal and zeros elsewhere. And now if you look at our matrix, we have each of these kind of, you could think that it's a sum of different I matrices and maybe multiplied with some value and added up. So for instance, I would say that this is a sum of many matrices, which is like, for instance, this 5, 5, 5, 5, and 5, and otherwise zeros. So for instance, this one I would create doing I5 times 5. So I5 would make 1s on the diagonal, but times 5 of course multiplies the 1s, but leaves zeros the way they are. And then to that matrix I would add, to that portion of that matrix, I would add, for instance, the respective I4 matrix. So I would have again I4 times 4, but it is added not directly to this one, so I cannot just make this plus this, because they are different size and we would get an error. But I can add this to a specific portion of my matrix in here. And then in a similar way, I could add a portion in here, and a portion in here, and a portion in here, every time having each of them smaller and then multiplied by a smaller number. And so that would let us create this upper triangle, and then we would take care in a similar way, take care of the bottom. So let's try to go into the code and see how that is done. So let's start from making the base I matrix, and I'll stick with n equal 5 just for now, so that the outputs we are getting are familiar with what the task is asking, but then we will test it for bigger cases. So I will call my resulting matrix A, and I know that now that the diagonal I can create just by doing something like that. So I create I matrix, which creates 5 1s on the diagonal, and then I multiply it by 5 in this case. Okay, so my A now is, just as I said, 5s on the diagonal and zeros elsewhere. And now I have to think, how can I add those smaller portions? So I will first write it without the loop, and then when I have the case for the 4s done, I'll think how to convert it into an indexed way, which can be done in the loop for the rest. So what will be now the portion of matrix that I am adding things? So from matrix A, I would like to access all the columns or first about the rows. All the rows from first one up to fourth, and all the columns from second until the last one, so I would use end. And to that portion, I would like to add something. So that means that I will again pick that portion because I want to know what are the original values in that portion of the matrix, and to it I would add I 4 and multiplied by 4. So this is how it would look if we were to do it manually. Now let's see what that brings. So you see I actually got the 4s up there. Now if I was to continue manually, and I would like to fill up now the next small diagonal, so I would want to visit rows from 1 to 3, because it would be now this small square here, from 1 to 3, then the columns from third till the last. Oh, sorry, I'm changing in the wrong place. This was 4 in here. So once again, first 3 rows and then columns from third till the last. Then again, this address which I am trying to modify has to appear here. So it's these elements that I pick out from my matrix. Then to those I add this small I matrix. And this new result I put back from where I picked that small portion of the matrix. So this is a similar trick what we had in the tasks, where you modify particular elements of the vector while preserving the rest. So now we can start to look for patterns. What is actually happening here? What is changing? And how I can make a loop do it for me and not do things manually. So first of all, to take care of this upper triangle, yeah, let's run maybe this first also, and so you can see that it actually is doing the job. Yes, so you can see the phrase now. So for this case, I need to do 4 times something like that, because I need to do the 4s, 3s, 2s, and 1. Now 4, how does 4 relate to my n? N is 5, and I need to do 1 step less than what n is. So I know that my I will be changing from 1 to n minus 1, because this is how many steps I need to do the upper triangle. And actually it will be the same number of steps to do the lower triangle. All right, so I know how many steps. Now I have to think what I'm actually supposed to do. So the answer is this actually. This is what I am supposed to do, but I don't want this to be done, like in this case, only for 4. I want it to be done for any I. And so here we can already see kind of the relation that when we were doing the first step, we were having here from 1 to 4. So this 4 again is like n minus 1 for the first step, but it was n minus 2 for the second step, and so on. And since I is the one representing our steps, it simply means that I have to put I in there, because there will always be one kind of row and column smaller matrix to be looked at. And that also means that there will have to be I there. Similarly, I can put I in here, because that's exactly, or not actually, not I, but when I is 1, I actually have to put a matrix 4 by 4. When I is 2, it's 3 by 3. So it's a complement of 5. So that means n minus I in here. And it's the same n minus I that has to be in here. Remember to use parentheses in here so that you actually multiply by n minus I and not just by n, and only then subtract I. So once again, when I is 1, this means that in here I will have n minus 1, which is 4. If I is 2, this becomes n minus I, which is 3, and so on. And again, I just realized that in here I shouldn't have had I, but n minus I, because that's also that number, that relation that we have in here. So it should be also n minus I in this place. The last thing to be taken care of is this, because now if we keep it at 2 up to n, we always have kind of n minus 1 columns, but we don't want n minus 1 columns, we want as many columns as is left up to our n. So for the first step, we were doing columns from second till the end. For the second step, from third till the end. So you can see that this one is always bigger by 1 than our index. So that's why in here I will use I plus 1, and in here as well, I plus 1. So let's close this one. I will also comment these 2 lines I wrote before, and let's check if it's actually doing what it should. Okay, and we ask for A. So you see now we do have this upper triangle filled up with what we want. Now we would need same kind of loop to do the lower triangle. And since we know also that for the lower triangle we need 4 steps, we don't actually need another loop. We can use the same one and just write another line of commands which will be evaluated at the same time. So what will change now? Now the difference will be that we will be always needing columns from 1 to somewhere and the rows from somewhere till the end. So if you notice the pattern, actually, it would be enough if we swap these two, if we swap their places, because it will indeed mean that we now need rows from I plus 1 till the end and columns from 1 up to n minus I. So I will copy this piece I had and I will swap these indexing in here. So rows with columns. And this remains the same because it is that one smaller and smaller and smaller every time being added. So I will also ask for A in here and we run that. So now you can see that it is ready. And we needed just one loop to complete it instead of figuring out a nested loop to make one element at a time.